On page 5 of your notes, we're covering double replacement reactions, and this is when the positive and negative ions of two compounds switch places. So it is not the opposite of a single replacement reaction, despite what the name sounds like. This is really when you have two separate compounds, so for example, AB plus CD, and they're going to switch partners with each other. So similar to in your single replacement reactions, you're going to pay attention to which one is positive and which one is negative. So in this, your positive element would be who? A, because your cation always comes first, and then your negative element is B, because that comes second, and then I have C and D, so positive, negative. What typically happens in these reactions, and I want you to draw this for yourself so that you have it, is they're reacting in aqueous solutions. It's not always, but a lot of the times it is. So then what you'll end up with is you would have two ionic compounds that will both dissolve in the water and dissociate, which remember that means to break up and to form the ions that they were made of in the first place. So my A would be floating around with a positive charge, B would have a negative charge, and C would have a positive charge, and D would have a negative charge. So when I put both of these things together in an aqueous solution, or in our lab today we're doing them in little dropper bottles, so they're already like this is aqueous and that's aqueous to begin with, you just have free ions floating around. When they're floating around like this, they're going to be free to bump into one another and form new compounds. But it's only going to form compounds that are actually I don't want to say like chemically sound. It's going to be a positive and a negative ion every single time. So my positives are never going to go together because positive doesn't go with positive. Positive goes with negative. So I started with AB. So if I form AB, that means nothing happened. So for A to be part of a new compound, the only option is for it to go with D, because that's the only other negative one that's different than the original negative that it was with. It's not going to go with C because C is positive. So my new compound on my product side is going to be a combination of A and D, where A is still my positive and D is negative, so A has to come first. Meaning that B and C are going to be in a compound together, but you have to write it in a certain way. Remember who comes first? The positive one every single time, your cation. So in this case, my cation would be... Yes, that is a great question. So you do have to re-crisscross it every time. So in this case, I don't have actual numbers on them, so there's nothing to be crisscrossed, but if we'll do some examples and see how the crisscrossing works. But anytime you are making an ionic compound, it doesn't bring its subscript over to the new compound. You re-crisscross with whatever it has. So it will be A and D bonded with C and B in that order. The other way we'll look at it is that the outside ones go together, and then the inside ones go together. Cation, anion, cation, anion. So if I look down here, my sodium is the first cation. It is going to get with the outside anion, so nitrate in this case. So if I draw, I'm going to draw this example just like I drew that one by putting my ions in there. So we'll have like this is my water, just to show that all of this is going to be dissolved in water. When I put Na2S into water, make an aqueous solution of that ionic compound, I'm left with Na with little plus charges and S with little -2 charges. It keeps that -2 with it because sulfur has a -2 charge. Do y'all see where I got that from? Okay, so if you didn't, sulfur, you could also look up on the periodic table. That's one that has a predictable charge. So it has a -2 charge because that's what the periodic table says. The only time you actually have to pull it from the formula is when it's a transition metal or tin or lead. So then I have cadmium and nitrate. Cadmium has an oxidation number of what? +2. And nitrate is NO3, and it has a -1 charge. So when I have actual elements or actual compounds that are dissolved in water, they're going to be free-floating ions just randomly bumping into one another. So then we are able to predict who goes with who on the product side based on what we know about them. If sodium started with sulfur, sodium started with S2, or just with S, sorry, that has a -2 charge. Sodium is not going to bond to cadmium because cadmium has a positive charge. Sodium must bond then with who now? NO3. So sodium and NO3 get together, and when I put those two together, they keep their normal oxidation numbers to crisscross. So I'd have Na with a +1 charge and NO3 with a -1 charge, and then they crisscross, but we don't write the subscript of 1, and that's how I ended up with NaNO3. At the same time, cadmium is then going to get with sulfur. Cadmium has a +2 charge and sulfur has a -2 charge, so Cd with the +2 and S with a -2. When they crisscross, you get Cd2S2, but then remember that that reduces down to just CdS, and that's how we got that. Does that make sense so far? It doesn't matter. So you could write like NaNO3 plus CdS, or like whichever one comes first, doesn't really matter. What matters is within the compound, like cadmium has to be listed before sulfur because cadmium is positive, or sodium has to be listed first because it's positive. Same thing with over here. But as far as like on either side of the plus sign, you could list NaNO3 plus CdS and it's fine. That will affect your coefficients though, so when it comes to balancing, when you do this, you just need to make sure that you have the right coefficients in the right places. Was there another question, or are you just stretching back there? Got it. So notice that here, this nitrate has a subscript of 2 on it because it was bonded to cadmium that had a +2 charge. So we had 2 nitrates on this side, but we don't have 2 nitrates on that side because when we make the formula, it comes from crisscrossing it. So then we still need to balance it. I have sodium, sulfur, cadmium, and NO3 nitrate. On my reactant side, I have 2 sodium atoms, 1 sulfur atom, 1 cadmium atom, and 2 nitrates. On my product side, I have 1 cadmium, 1 sulfur, 1 sodium, and 1 nitrate. The good news is that these are typically pretty easy to balance. So right here, I have 2 sodiums and 2 nitrates on my reactant side. I need to get 2 and 2 on my product side, and they are together. So 2 times 1 sodium gives me 2, and 2 times 1 nitrate gives me 2. And then we are all balanced. Yes? Yes. Okay, so are you asking, like, they're randomly bumping into each other, so at the end, like, could I still have, like, cadmium bonded to nitrate? Is that what you're asking? Yes, and you often will. So, in this type of reaction, if we look at this one and we go back up to kind of where we stopped writing, double replacement reactions, things that are following this swapping partners kind of format, they fall into 2 categories. One of the categories is an acid-base reaction, and the other is called a precipitate reaction. And a precipitate reaction means that there is a precipitate formed, so you have to think about what you know about being a precipitate. An acid-base reaction is recognizable because it will always start with an acid as a reactant. In order for something to be an acid, how can you recognize that? Starts with hydrogen. So an acid has to be one of your reactants, and the products are going to be 2 things every single time. One is a salt, which means any ionic compound. So remember, salt just means cation, anion. It does not necessarily mean NaCl specifically, although that is a salt. So our salt, I'm just going to write ionic underneath that. And the other thing that is formed is water, but you'll usually see it as HOH. You could also see it as H2O. Either way, that is water. So an acid-base reaction, every single time, will have an acid as a reactant, and it will form both a salt and water. If it is not an acid-base reaction, then you are looking to see if it's a precipitate reaction. It might not be that either, and then we'll talk about that case in a minute. A precipitate reaction is a double replacement reaction where one of the products is a soluble salt, so a soluble, SOLUBLE, that means able to dissolve, and the other product is an insoluble salt. And you'll use the solubility chart on the back of your periodic table to determine if your products are soluble or insoluble. So that is this that we're talking about, the solubility of common ionic compounds in water. So soluble, that means able to dissolve, and then insoluble means not able to dissolve, and then that would make it the precipitate. So we'll talk about that in just a second. So knowing these two types of reactions, we've already established that this is a double replacement reaction. We have our products already formed for us. We've already balanced the equation. What type of reaction are we looking for here? Is this one going to be acid-base or precipitate? If anything, it will be precipitate. You can tell right away that it's not going to be acid-base because neither one of my reactants start with hydrogen, so neither one of these are acids. So automatically you can rule out that it is not an acid-base reaction. You see how I got that? Okay. Then we're looking to see, is this a precipitate reaction? In order for it to qualify as an actual precipitate reaction, a precipitate must be formed. And so by definition, a precipitate will always be a product. You're never going to have a reactant as a precipitate because your reactants are your starting materials. And because a precipitate is when a solid is formed, that means it's something that is produced. So you are only looking at things on your product side of the equation. So between CDS and NaNO3, I'm trying to figure out, is one of these things going to be a precipitate? And so precipitate is what happens when a product is formed from these two aqueous solutions. I dissolved my ions, they're all bouncing around. Precipitate is what happens when two of those ions, I guess, bump into each other, form a compound that is not able to dissolve in water. The word we use for that is insoluble. If that compound is not able to dissolve in water, it will precipitate out of the solution. It ends up looking like rain, like it will happen wherever it hits in the solution. So if they bump into each other up here, boom, they precipitate out and kind of just like trickle down, and that's when you collect solid at the bottom. So the way that I can determine that is by using my solubility chart. So we'll look at CDS first. So again, we only have to look at our products because I know that both of these are reactants and they will not be precipitates just by the very definition. CDS is one of the things that I produced. Most of the things that are listed on my solubility chart are anions. So I'm going to look it up by the second part. So CDS, my sulfur is the anion in this case. And if I go down my list, down, 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 sulfur is right here. Sulfur is found in the insoluble section. On your periodic tables, you can go ahead and write precipitate here. If something is insoluble, it is going to form a precipitate. And what state of matter is a precipitate? Solid. So then this is where the actual state of matter is going to come into play, where you're going to include that in your equation now. So a precipitate, that would form a solid. So if it is insoluble, it's going to form a solid. And then there are all these exceptions listed. If it falls into one of these categories, so if it's supposed to be insoluble, but then it's actually an exception to that, then it would be soluble, and then we would call that aqueous, AQUEOUS, or we would just write AQ or just write S for solid. So down here, sulfur is in my, what? Because it's like whatever it's bonded to. So like carbonate is mostly going to be insoluble unless it's bonded to one of these. Phosphate is mostly going to be insoluble unless it's bonded to one of these. So that's how you read that. So sulfur is going to be mostly insoluble unless you're bonded to one of these. In this compound, is it sulfur bonded to one of the exceptions, or is it just sulfur as it? So it's sulfur bonded to cadmium, which is not an exception. So we truly are in the insoluble section, which tells me that this compound would be my precipitate. So I would show that by putting an S in parentheses. So similar to how the AQ is already there for you, I would put an S in parentheses after this. Sometimes on your quiz or your test, I'll ask you to write the precipitate on a line, or I'll ask you to circle your precipitate. Just do whatever it asks. But if you were going to show it in this format, generally putting a little S there is how I would indicate that. So this is my precipitate. And then just to be sure, check your other product and see, does that form something else? Did you maybe check something wrong, forget an exception, something like that? NO3 is my anion here, so if I look up NO3, nitrate is soluble, and there are no exceptions to that. So anytime you have nitrate in your compound, that is going to be soluble, meaning it is not your precipitate. So this would just be an aqueous solution, AQ. So what that means is that when I have these compounds reacting together in an aqueous solution and they randomly are bumping into each other, my sodium is going to bond with my nitrate, but they're not actually bonded because they're dissolved in water, so they're going to be dissociated. They're going to be in their ionic form like this. And then cadmium and sulfur, when they hit each other, the second that these two come in contact with one another, they form a solid and they will come out of the solution, meaning they are no longer dissolved. They will clump up together and they will precipitate out of the solution, and that is when you're left with solid at the bottom of your thing. So then you don't have any cadmium ions and you don't have any sulfur ions left because it would precipitate out and form a solid. So solid means it's no longer in its ionic form, or it's no longer it is ionic, but it's not in an ion form here. It's not dissolved. What does last what say? I haven't gotten there yet. Questions on this part so far? Does it make sense? Alright, let's keep on going. Yes, you will have your entire periodic table on your test. Probably on your quiz, I'll just take off this whole chunk, that's your polyatomic ions. On your test, though, you'll have them, and even on your quiz, though, when I take off those, you'll still have the formulas for you, so you should be fine. Alright, let's try this one. So I have FeS and HCl. So FeS is iron what? Iron... It is iron sulfide, but you need a number in there. Iron 2 sulfide. Perfect. So this is iron 2 sulfide reacts with hydrochloric acid to form something. I kind of took over some space there, so we'll just... So it will go iron with chlorine and then hydrogen with sulfur. So iron, it's iron 2 sulfide, and I can tell because if I undo the crisscrossing, I know sulfur has a negative 2 charge, so iron must have started with a positive 2 charge to reduce down. So iron with a plus 2 charge bonding with chlorine that has a negative 1 charge. When they crisscross, what's my new formula? Perfect. FeCl2, and then my next compound would be a combination of hydrogen and sulfur, so H2S. Perfect. So these are my two new compounds that I have made, and then I look at this, and when I look at it personally, the way that I try to figure it out is it acid-base, yes or no? And if the answer is no, then you look at precipitate. So I do have an acid in my reaction. Does that make it acid-base? If it starts with an acid and the products are salt and water. I do have an acid as a reactant. Are my products salt and water? No. This is a salt. That's, I guess, technically kind of also a salt, but not really. Definitely not water. So you're like, I think that water is the easiest one to look for. You should just get into the habit of recognizing that one. If you see water, acid base is what you should be thinking of. But here we did not produce a salt and water. So that means it is not an acid-base reaction. What kind of reaction would this have to be then? Precipitate reaction. If it is a precipitate reaction, then it would have a precipitate. So I'll look at this one and see, okay, I know that neither of these are going to be precipitates. Even though this says solid, that does not mean it's a precipitate because it's one of my reactants. So by definition, a precipitate is a solid that you are making, a solid that is formed from the reaction. So FeCl2 is the first thing I'm looking up. My chlorine is right here. It is in the soluble section, so I just double check and make sure, are there any exceptions that I have to be worried about? Iron is not on that list. So My chlorine compound, is that going to be soluble or insoluble? Soluble. So the letters that I need to write down next to it are AQ for aqueous, and then H2S. I would look up sulfur. It is in the insoluble section, but again, double check and make sure you're not bonded to one of my exceptions. Definitely not bonded to NH4. Am I bonded to an alkali metal cation? Do you remember what an alkali metal is? At least you're honest. Alkali metals are who on our periodic table? Alkaline earth metals are the second group, and alkali metals are the first group. So, these are your alkali metals. Group 1. So, my question remains, in this compound where I have H2S, I have sulfur, is it bonded to an alkali metal cation? Hydrogen is not included. I even skipped hydrogen when I was circling it just to see if y'all paid attention. No, hydrogen is still a nonmetal. So hydrogen acts like a metal in the sense that it's positively charged. It will replace other positively charged atoms, but it is not a metal, so it does not count as an alkali metal cation. So H2S, that is truly insoluble, so I would put S next to it, meaning that is my solid. I would circle it. This is my precipitate. And if we were identifying the type of reaction of this one, this would be double replacement. I'm going to abbreviate it DR, double replacement, and this is precipitate. So it classifies as both. And then same thing with this one. This one is also double replacement precipitate. So DR for double replacement, and then precipitate.